Welcome back to the deep dive. Today, we're not just scratching the surface. We are plunging headfirst into a world that exists silently beneath our fingertips, a hidden battlefield unfolding inside the digital devices we rely on every single day.
Yeah, absolutely. From the smart card tucked into your wallet,
Yeah.
ensuring secure transactions.
Right, or the phone you hold in your hand, packed with your most personal data. These gadgets are under constant, often invisible attack.
They really are.
And here on the deep dive, our mission is to explore not just the nature of these insidious threats, but also to reveal a truly cutting-edge solution designed to protect them at their very core. Okay, let's unpack this. We're going to understand how to fortify these digital guardians, our chips, against increasingly sophisticated electromagnetic assaults. It honestly sounds like the plot of a high-tech spy movie, but I assure you, it is very real, and the stakes couldn't be higher for all of us.
Definitely.
Our journey today is anchored in some truly groundbreaking research, a paper titled Electromagnetic Analysis of Integrated On-Chip Sensing Loop for Side Channel and Fault Injection Attack Detection by Ghosh et al.
A bit of a mouthful, but yeah, really important work.
It is. This paper introduces an innovative, almost revolutionary on-chip sensor that could redefine device security as we know it. Our mission, then, is crystal clear: to illuminate these silent, invisible threats constantly probing our devices, and then to present an elegant solution that promises to safeguard our sensitive data without adding any extra bulk, cost, or complexity to our beloved technology. It's about giving our chips a sense of self-preservation, really.
And that mission, as you rightly say, is incredibly crucial for you, our listener, because the integrity of your digital life literally hangs in the balance. Think about the data on your smartwatches, the confidential information on your personal computers, the private conversations and financial details stored on your mobile phones. I mean, any device that holds sensitive information is a target.
It really brings it home when you list it like that.
It does. And what's truly fascinating, and perhaps a bit unsettling here, is that even cryptographic algorithms, which are the digital locks designed to be computationally secure against brute force attacks, aren't perfectly impenetrable. They leak information.
Leak information.
Yeah.
Not through the math, right?
No, not because of a flaw in their mathematical design, but through the inherent physical processes of computation itself. It's kind of like the act of thinking out loud, where the very process of formulating a thought leaves subtle physical clues. These subtle leaks manifest primarily through two main attack vectors that we need to understand: electromagnetic side channel analysis, or EMSCA,
EMSCA. Okay.
and fault injection attacks, which we'll refer to as FIAs.
FIS. Got it.
Now, imagine EMSCA as a form of highly sophisticated digital eavesdropping. An attacker doesn't need to physically break into your device, no lockpicking or hacking software required.
So hands off, basically.
Exactly. Instead, they can simply listen to its subtle electromagnetic whispers from a distance to deduce sensitive information, things like your encryption keys, without ever touching the device.
Wow. Just listening in.
On the other hand, fault injection attacks are about tricking the system. These involve deliberately disturbing a device's normal operation, perhaps with a fleeting voltage glitch, a quick spike of laser light, or even a sudden burst of microwaves.
So actively messing with it.
Actively messing with it, yeah. To make it malfunction just enough to reveal secrets it would otherwise keep private. It's about temporarily confusing the chip into giving up its guard. The popularity of these attacks is unfortunately soaring, largely due to their relative simplicity and low cost. We're not talking about nation-state actors needing millions in equipment. With a few $100s and some specialized but readily available tools, things you could find online, someone with a bit of know-how can attempt to snoop on your device.
Just a few $100s. That's alarming.
It is. And this reality underscores the urgent need for robust, integrated countermeasures built directly into the hardware of our devices.
That's a powerful and genuinely unsettling thought. The idea that someone could potentially compromise my phone or smart card without physically interacting with it, using relatively inexpensive equipment, really brings home the scale of this microscopic battlefield. So let's dig a bit deeper into this invisible war. What exactly are these EM emanations, these invisible whispers you mentioned, that can compromise security? The source material is quite explicit, telling us that data can be easily snooped from a distance by simply using a cheap EM probe. Imagine that. Just a cheap probe held near your device, and suddenly its secrets are no longer your own. It sounds almost too easy.
It does sound easy, and that's the worry. The probes themselves aren't necessarily complex.
And it's not just about passively listening in. The paper also highlights differential fault attacks, DFAs, as a specific, particularly insidious type of FIA. These attacks, as the research indicates, can deduce sensitive data through glitch injection. So we're dealing with both passive eavesdropping and active interference.
Correct. Two distinct but equally dangerous threats.
To give you a clearer, more visceral picture, imagine your smart card or your phone as if it were a person. In one scenario, it's whispering its deepest secrets through invisible waves that an eavesdropper can pick up from across the room with just a basic, low-cost listening device.
Like unintended signals, yeah.
In another, a mischievous, skilled attacker briefly startles or confuses it, perhaps with a quick, targeted jolt of electricity, causing it to blurt out crucial information it was supposed to keep private information, like a cryptographic key.
That's a good analogy. The glitch forces an error, and sometimes that error reveals something important.
That's the level of stealth and ingenuity we're up against in these digital attacks, and why we need equally ingenious defenses.
To truly grasp why these EM leakages occur, we need to consider the fundamental physics at play within modern microchips. Today's crypto coprocessors, the parts of your device responsible for handling sensitive encryption, from your banking app to your messaging, are implemented using what's broadly known as CMOS technology.
CMOS, right. That's pretty standard stuff in chips, isn't it?
Absolutely. Now, for our listeners, while you likely know it stands for complementary metal oxide semiconductor, the key takeaway is that it's the industry standard for creating the incredibly tiny, efficient switches, the transistors that power everything. And these tiny switches are operating at astonishing speeds, billions of times per second.
Billions. Wow.
At its core, the operation of these circuits involves the rapid movement of electrical charges as these transistors switch on and off. This constant dynamic movement of charges inherently creates time-varying electric field. It's like a tiny electrical symphony playing out across the chip.
An electrical symphony, I like that.
And this isn't just a random occurrence. It's a direct consequence of fundamental physics, beautifully described by Maxwell's relations. Essentially, if you have moving charges or oscillating currents, J, as the paper puts it, and changing electric fields within the chip, you will inevitably generate a time-varying magnetic field, H.
Ah, the famous Maxwell's relations. So electricity and magnetism are linked.
Intrinsically linked. What this means in plain terms is that every time your chip performs a calculation, especially a sensitive cryptographic one, it's not just doing math. It's also generating a tiny, fluctuating electromagnetic field that radiates outwards, like subtle ripples in a pond.
So the very act of computing creates these signals.
Precisely. From an attacker's perspective, these EM emanations aren't just electrical noise or random signals. They carry meaningful information. They are a subtle, physical byproduct of the chip's digital operations. With the right tools and advanced analysis techniques, an attacker can analyze these patterns to decipher cryptographic keys, personal identification numbers, or other sensitive data, effectively listening to the chip's inner workings.
So they're decoding the ripples, essentially.
In a way, yes. The paper does mention that existing countermeasures have been explored. Things like circuit-level protections designed to mask these EM emissions, specific architectures for attack detection, and even capacitive asymmetry sensing techniques that try to balance out the signals.
So people have tried to fix this before.
Oh, absolutely. It's an active area. However, the critical point is that these are still areas of active research and constant improvement, because the attackers are always evolving their methods. It's an ongoing arms race.
Right. Constant cat and mouse game.
It really is. And this raises an important question for us. How can we detect these subtle, often invisible attacks directly on the chip itself in a way that is robust, energy efficient, and doesn't add complexity or cost to the manufacturing process?
And that's precisely where the innovation comes in, taking us from understanding the problem to exploring a truly ingenious solution. Here's where it gets really interesting. The researchers in this paper have developed what they call an on-chip sensing loop.
The core idea.
It's an incredibly clever and surprisingly simple answer to a very complex and persistent security problem. The true beauty of this design lies in its sheer elegance and practicality. It's described as a higher metal layer loop-based zero-area overhead sensor. Let's break down why zero-area overhead is such a game-changer, because it's super important.
It absolutely is. Chip real estate is incredibly valuable.
Exactly. In chip design, every square micrometer of silicon is precious real estate. Adding new security features typically means adding more components, which increases the chip size, cost, and power consumption. But this sensor doesn't do that. Zero area overhead means the sensor doesn't take up any extra valuable space on the chip. It's effectively integrated into existing, unused metal layers, like a silent guardian nestled right into the very fabric of the chip, using what would otherwise be empty space.
Yeah, it's just a passive loop in an upper metal layer, often metal 9 or above, which frequently isn't used for critical signal routing.
It's an incredibly efficient use of resources. And this sensor has two main powerful goals. First, to detect the subtle electromagnetic coupling that naturally arises from transistor switching activity, and to immediately register any effects of fault injection attacks.
So sensing the internal state, essentially.
Right, and second, to detect changes in that electromagnetic coupling that would indicate an approaching probe, someone trying to stealthily snoop on your device from outside.
Detecting the external threat, too.
It's like giving your chip an innate sense of awareness, allowing it to feel when something is amiss internally, or when a malicious listener is getting too close externally.
Exactly. The mechanism behind this on-chip loop cleverly leverages another fundamental principle of electromagnetism, Faraday's law of induction.
Faraday's law. Okay, how does that work here?
To visualize this, let's go back to those oscillating currents and time-varying magnetic fields we discussed earlier, emanating from the crypto coprocessor's rapid switching activity. Imagine these tiny, fluctuating magnetic fields constantly rippling outwards from the heart of the chip. Okay, got the ripples. Now, if a small, specifically designed metal loop is intentionally placed in one of the higher metal layers of the chip layers that aren't typically used for active circuit routing, essentially, empty space Faraday's law dictates what happens. It states that the time-variant magnetic flux generated due to CMO switching induces an electric field across the length of the loop as given by Faraday's law.
So the changing magnetic field creates an electric field in the loop.
Precisely. In simpler terms, those tiny fluctuating magnetic fields from the chip's operations will generate a small oscillating voltage in this strategically placed metal loop. It's like a miniature antenna, but instead of picking up radio waves from the air, it's picking up the chip's own internal electromagnetic signature, its own subtle hum.
A tiny antenna listening to itself. That's
Yeah.
neat.
It is. The research paper visually represents this, and if you were to look at Figure 1 in the source, you'd conceptually see how the chip's dynamic switching activity, labeled V-switching, directly induces a distinct oscillating voltage pattern, VLOOP, within this clever sensing loop, almost like ripples spreading from a stone dropped into a pond, detected by a float.
Okay, so V-switching causes VLOOP, a direct link.
A direct link, yes.
Yeah.
And the crucial insight here, and what makes this so powerful, is that due to its proximity to the crypto coprocessor, such a higher metal layer on-chip loop should be highly sensitive to the dynamics of CMOS circuit operations and be able to detect sudden changes in temporal behavior. Think of it as the chip's incredibly sensitive nervous system. Any significant alteration to its internal electromagnetic environment, whether that's from an internal malfunction caused by an attack or an external intrusion, will immediately be registered and reflected by the voltage induced in this loop.
So it's really tuned in to what's happening right next to it.
Highly tuned in. And one of the key advantages that makes this truly groundbreaking is that this attack sensing technique is completely passive. It doesn't require any active components, no power-hungry transistors constantly running, and no excitation signals.
No extra power drain. That's huge for mobile devices.
Huge. This makes it incredibly energy efficient, a critical factor for battery-powered IoT devices, smart cards, and mobile electronics, where every milliwatt of power is precious.
That's brilliant. So this tiny passive loop becomes an integral part of the chip's self-defense system, almost like an intrinsic alarm. Let's delve into the first type of attack it can detect, fault injection attacks. How does this clever, nearly invisible loop detect something as fleeting and specific as a voltage glitch, which is often used in these attacks? The paper explains that a voltage glitch is essentially a sudden drop in VDD, where VDD is the main supply voltage for the circuit. This isn't just a minor power fluctuation, it's a deliberate transient dip designed to starve the chip of power for a split second.
Right, a very short, sharp drop in the power.
This sudden drop in voltage has a very specific critical effect. It reduces switching activity of the circuit. Basically, for a fleeting moment, the chip isn't getting enough power to perform its operations correctly or at full speed.
The transistors slow down, or maybe don't switch properly at all for that instant.
So if the loop is constantly monitoring the EM emanations from the switching activity, those tiny electrical whispers, then a sudden reduction in that activity directly caused by the voltage glitch must show up in the loop's induced voltage, right?
Logically, yes. Less switching should mean less induced voltage.
This change in V-switching causes a change in induced loop, and that detectable change in the induced voltage pattern is precisely the key to detecting these insidious fault injection attacks. It's the chip essentially saying, hey, something just felt wrong here.
Exactly. The paper describes this scenario as detecting an EM signature from FIA, varying input, constant transfer function. In this specific case, the fault injection, like a voltage glitch, alters the input to the system. It disrupts the stable power supply, which then directly impacts the normal switching behavior of the CMOS transistors.
Okay, so the input power varies, but how the signal travels transfer function stays the same.
Right. To thoroughly test this concept before even fabricating a chip, the researchers used a sophisticated simulation approach. They took the layout of an AND gate, a very basic logic gate that's a fundamental building block of microchips, and imported it into a highly specialized electromagnetic simulation software called ANSYS HFSS.
HFSS, high frequency structure simulator, something like that.
Exactly. If you imagine looking at Figure 2a from the source, you'd see a conceptual representation of this. Think of ANSYS HFSS as a virtual lab, where they can precisely model electromagnetic fields, allowing them to predict how signals and interference behave at the microscopic level before a single physical chip is even made. This is crucial because it lets them visualize and predict the invisible whispers emanating from the chip's operations, giving them a roadmap for where attacks might occur and how their sensor would react.
So they can test the idea before spending money on silicon.
Smart.
Very smart. Within the simulation, they provided a sinusoidal excitation to mimic the actual powering and rapid switching that happens in a real chip. They could even enable or disable individual transistors using parameterized resistors, simulating the dynamic active switching of the circuit. The crucial part was how they integrated the sensor. The loop is implemented in metal 9, as shown in Figure 2b. Picture it like this. The loop is strategically woven into the very top layer of the chip, metal 9, sitting just above the active circuit layers, almost like a tiny antenna overlooking the chip's bustling activity. Okay, so the simulation setup mimics the real thing closely. What did it show?
The simulations clearly illustrated the impact of a fault injection attack. When no voltage glitch was present, the induced voltage in the loop, VLOOP, exhibited a certain stable pattern, which you can visualize conceptually as a clean, predictable wave in Figure 2c.
Normal operation, normal signal.
Right. However, when a voltage glitch was introduced, causing that sudden momentary drop in VDD and the subsequent reduced switching activity, there was a dramatic and immediate change. Specifically, the VLOOP amplitude reduced significantly during the exact moment of the glitch injection, as depicted in Figure 2c.
Ah, so a clear dip in the
A
signal.
very clear dip. This clear and distinct difference in the induced voltage pattern is precisely what the on-chip sensor is designed to pick up. By continuously monitoring this pattern, the chip can effectively detect the presence of a fault injection attack. If we connect this to the bigger picture, this directly addresses the core of differential fault attacks by detecting the very malfunction or temporary disruption they exploit to extract sensitive data.
It spots the glitch itself.
It spots the effect of the glitch on the chip's EM signature. Yeah. It's like giving the chip an instantaneous internal reflex to sense when it's being tampered with, allowing it to potentially halt operations or trigger a protective measure before any data is compromised.
That's incredibly clever. It's literally feeling the disruption from within, almost like a digital nervous system detecting an internal malfunction. But now, let's shift our focus to the other major threat. The snooping from a distance attacks, the EM side channel analysis. Can this same ingenious loop detect someone trying to listen in? Or does that require a completely different mechanism? The paper clarifies this by explaining that when an external EM probe, intending to perform EMSEA, is brought in close proximity to the system, the probe disturbs the EM fields generated from the CMOS switching.
So the probe itself interferes.
Right, so it's not just about the loop passively picking up the chip's own emanations. It's about detecting an external object interfering with and subtly altering those emanations. So what does this all mean for the loop's induced voltage? How does an external probe, even if it's not physically touching the chip, change what the internal sensor observes, and what kind of signal does it create?
This is where the concept of the EM signature from approaching probe, varying transfer function, constant input comes into play, and it's a crucial distinction from fault injection attacks.
Okay, varying transfer function. How's it different?
Unlike in FIA, where the chip's input voltage is suddenly altered, here, the chip's internal operation, its input, remains perfectly constant. The chip is running normally. What changes is the transfer function itself, meaning how the chip's internal EM fields propagate and are ultimately received by our on-chip loop. The mere physical presence of an external object, like an EM probe, directly affects this electromagnetic propagation, subtly altering the environment around the chip.
So the probe changes how the sound travels from the chip to the loop, even if the sound itself is the same.
That's a good way to put it. To accurately simulate this, the researchers meticulously modeled a commercially available H-field probe, Langer ICR HH127, diameter 100 dim, as shown in Figure 3A.
An H-field probe that measures the magnetic field, right? And 100 microns, that's tiny.
Very tiny, yes,
Ugh.
magnetic field. And this miniature size is crucial because attackers often use such small probes to get as close as possible to the active circuits on a chip without physically damaging it. What they observed in their simulations was quite telling. The probe disturbs the local fields, hence modifying the TF itself, again causing a change in loop, which can be sensed to detect EMSEA. Essentially, the external probe acts like a tiny localized distortion in the EM field, and this distortion in turn subtly but measurably alters the voltage induced in our on-chip loop.
So the loop senses this distortion caused by the probe.
Exactly. The simulations clearly demonstrated that the voltage pattern changes with the distance of the probe from the IC, and, critically, higher gain is observed at a lower distance of probe from IC, as shown in Figure 3B.
Higher gain, meaning a stronger signal in the loop when the probe is closer?
Yes, a stronger induced voltage. This means the closer the probe gets to the chip, the stronger and more pronounced the induced voltage in the internal loop becomes, making detection even more reliable. The transient simulations, depicted conceptually in Figure 3C, showing the loop's output without the probe, and Figure 3, showing the output with the probe positioned at a 1 millimeter distance, further reaffirm the fact that a higher gain in loop is observed even if the probe is kept at 1 millimeter distance.
1 millimeter, that's still pretty close, but definitely not touching.
Right, it's a practical distance an attacker might use. This is incredibly significant because it means the sensor doesn't need the probe to be directly on top of the chip to detect it. Detection can occur from a realistic distance.
Okay, but why does the probe increase the voltage in the loop?
The underlying reason for this phenomenon, as explained in the paper, is that part of the emanated fields are scattered and confined by the cylindrical structure of the probe, resulting into an increase in the induced voltage in the loop.
So the probe kind of focuses or reflects some of the chip's own EM field back towards the loop.
Sort of, yes.
Yeah.
It alters the local field distribution. So the probe isn't just passively listening. Its physical presence actually interferes with and alters the electromagnetic landscape around the chip. Our on-chip loop is sensing that specific malicious alteration, almost like the chip feeling a tiny magnetic presence hovering near it.
Feeling its presence. Spooky.
A little, yeah. It's important to note that the induced voltage in these initial simulation results was in the millivolt MV range, but that's because only one gate is simulated for simplicity.
Ah, right, just one tiny component.
Exactly. The researchers correctly anticipate that a real encryption engine, like the AES-256 they later tested, which contains nearly 14,300 gates, would produce a superposition of all these individual gate activities, generally contributing to a much higher, more easily detectable induced voltage, which would make detection even more robust in a real device.
Okay, more gates, more activity, stronger signal overall. Makes sense. That's a vital distinction, moving from a simplified simulation to the complexities of a real functional chip. Simulations give us a theoretical understanding and prediction, but the real test is always in the hardware. So theory is one thing, but does this actually work in the real world? Let's dive into the real-world validation, the measurement results that truly bring this innovative sensor to life. The researchers, in their commitment to real-world validation, put their theory to the test by fabricating a 65mm CMOS test chip with parallel AES-256 encryption engine.
A real chip running real crypto.
Exactly. This isn't just a generic chip. It's a sophisticated actual chip designed to perform advanced, widely used encryption, providing a highly realistic and challenging environment for testing. And here's that crucial, groundbreaking detail again, the zero area overhead advantage.
Can't stress that enough.
Metal 9 of the IC is used to create the on-chip loop, and significantly, Metal 9 is not used for routing of the circuit. This means the sensor is integrated without compromising the chip's core functionality or adding to its physical footprint. It's truly an invisible, integrated guardian.
Using otherwise wasted space. Very clever.
The test chip itself is no slouch. It consumes 0.78 milliwatt power running at 50 megahertz clock at 0.8 V supply voltage. This is a low-power, high-performance component, making the passive, energy-efficient nature of our sensor even more impactful.
Yeah, 0.78 milliwatts is pretty low power for an AES engine running at 50 millihertz.
The chip was integrated using chip-on-board packaging on a printed circuit board, PCB, which you can visualize conceptually from Figure 4B and C in the source. A complete functional setup, meticulously prepared for rigorous real-world testing.
Okay, so they built the actual thing. The measurement setup was quite comprehensive, designed to replicate both types of attacks we've discussed with real hardware. To precisely control the data going into the chip, a computer controls an NIDAQ card to send the input plaintexts through the scam chain interface of the circuit.
NIDAQ, that's for controlling and measuring signals accurately, right?
Exactly. For those unfamiliar, a NIDAQ card is essentially a specialized interface for data acquisition and control, allowing engineers to precisely interact with hardware. And the scan chain interface is a common, built-in way to test and configure the chip's internal logic, providing direct access to feed in specific plaintexts the data before encryption. This ensured they could perfectly control the chip's operations for testing.
Full control over the inputs. Good.
For the FIA injection, a precisely configured power supply is used to inject a glitch in VDD of the chip. They specifically used a voltage glitch of 0.4 V for voltage glitch attack, a targeted and realistic perturbation designed to temporarily disrupt the chip's power supply.
A 0.4-volt drop, significant enough to cause trouble.
Potentially, yes. For the EMSCA probe setup, a 10mm H probe located at a distance of 1 millimeter is used for this experiment.
Wait, 10 millimeters? That's much bigger than the 100-micron probe in the simulation.
Good catch. Yes, they use a larger, perhaps more readily available or standard lab probe for the physical experiment. Still positioned 1 millimeter away, though, this simulates a realistic scenario where an attacker might position a commercially available magnetic field probe just above the chip, trying to eavesdrop.
Okay, different probe but same distance. And how did they capture the loop's signal?
Finally, the traces collected from the on-chip loop using a 400 ANSPICE oscilloscope were sent to a PC for further processing. That's 400 megasamples per second, meaning this oscilloscope can capture incredibly fast, fleeting electrical changes, which is absolutely vital for catching the subtle electromagnetic whispers and disruptions we're discussing.
Super high-speed measurements needed. Okay, so what did they find? Let's start with the fault injection attacks. Did the real chip match the simulation?
Now on to the measurement results for FIA. The real-world data beautifully confirmed the simulation predictions, proving the concept in actual silicon. In Figure 5A, from the source, you can clearly see both the inserted glitch and induced voltage pattern. The critical observation was undeniably clear. The amplitude of the induced voltage reduces at the time of the glitch injection. This directly validates that the on-chip loop is indeed sensitive to these momentary voltage drops and can reliably detect fault injection attacks as they happen.
So, just like the simulation predicted, a clear drop in the loop's voltage during the glitch.
Exactly. It's a direct physical confirmation of the theoretical model. Pretty neat.
Very neat. Okay, so FIA detection works. What about the trickier one, detecting the approaching probe for EMSCA? You mentioned noise could be an issue.
Right. The measurement results for EMSCA presented a unique and common challenge in real-world measurements. While, as predicted, the AES engine with its 14,300 gates did contribute to a higher induced voltage compared to the single-gate simulation, because there's far more activity producing EM signals. Measurement noise creates difficulty in differentiating the probe's presence in raw traces.
Ah, so the signal was stronger, but the noise was too. Made it hard to see the effect of the probe.
Precisely. The real world, unfortunately, isn't as clean and pristine as a simulation. There's always ambient electromagnetic noise, and the chip itself can generate various forms of interference. It can mask subtle effects.
So how did they deal with that? Did the sensor fail then?
Not at all. The researchers, demonstrating true engineering ingenuity, employed an intelligent post-processing solution to overcome this noise. They didn't just take one reading. Instead, they rigorously collected 10 traces for both in the presence and in the absence of the probe. To ensure absolute rigor and minimize ambiguity, they meticulously collected each trace with the same input plaintext and same key. What's more, each trace is collected by averaging 1,000 same encryption, same plaintext, and same key for both the cases.
Whoa, okay. 10 traces, and each trace was an average of 1,000 runs. That's a lot of data.
A huge amount of data. 10,000 runs per condition, probe, present, probe absent. This extensive averaging process, repeated thousands of times, helped to effectively filter out random noise and highlight the subtle but consistent signal that indicated the probe's presence. It's a testament to thorough scientific methodology.
Averaging out the randomness to find the real signal. Clever.
Very clever. The ultimate metric they used to cut through the noise was the mean of absolute value of a coupled voltage. When they plotted these meticulously processed results, as shown in the bar graph of Figure 5C, the difference was undeniable. This clearly shows higher induced voltage in presence of an EM probe.
Ah, so after all that processing, the difference became clear. Higher voltage with the probe nearby.
Exactly. Despite the inherent challenges of real-world noise, this intelligent processing allowed the sensor to effectively detect the presence of an external EM probe. If we connect this to the bigger picture, this real-world validation is absolutely crucial. It proves that the theoretical concept and the simulation predictions hold up against the messy, complex challenges of practical implementation. This isn't just a lab curiosity. It's a proven method for enhancing hardware security, ready for real-world application.
It works in the real world, even with noise. That's fantastic.
This shows the potential to secure devices that currently have no real-time protection against these physical attacks.
That's truly remarkable. The leap from theoretical models to robust real-world detection, even in the face of noise, is a testament to groundbreaking research. So, what does this all mean for the future of our digital devices, from our smartphones to the countless IoT gadgets populating our homes and cities? We've seen today how a surprisingly simple, zero-area overhead metal loop, integrated right onto the chip using existing layers, can act as a silent, ever-vigilant guardian. It's not just a clever trick, it's a testament to deep understanding of physics and ingenious engineering.
It really is elegant in its simplicity.
This research has delivered on two critical fronts. First, effectively detecting fault injection attacks by utilizing the induced voltage pattern that changes when a glitch occurs, giving the chip an internal sense of being tampered with.
Check. FIA detection works.
And second, reliably identifying an approaching probe for EM side channel analysis by sensing the induced voltage change in its presence, acting like an external proximity sensor.
Check. EMSCA detection works too with some smart processing.
What's truly significant here, and what gives this research immense weight, is that for the first time, the results from an integrated EM analysis framework are validated through measurements of a custom IC. This isn't just theoretical musing, it's proven in silicon on a real encryption engine.
That's the key takeaway. From theory through simulation to actual hardware proof.
This paves the path to identifying low-cost circuits that could be used for on-chip detection, ultimately making our devices inherently more secure at their very foundation.
Indeed. This raises an important question. How will this kind of on-chip self-awareness transform hardware security in the future? We're moving beyond mere software patches and external firewalls to a world where the very silicon beneath your fingertips can inherently sense and react to threats.
Self-aware silicon. I like the sound of that.
It represents a fundamental shift towards more robust, ubiquitous protection, especially vital in our increasingly connected world. Think about the explosion of IoT devices. Smart home gadgets, connected cars, medical wearables, industrial sensors. Each of these presents a potential attack surface, often operating in environments where physical access is easier, making them prime targets for side channel and fault injection attacks.
Yeah, those little devices often don't have much built-in protection, do they?
Often very little, especially against these kinds of physical attacks. With this kind of integrated sensor, every smart device you own could intrinsically sense and warn you about attempts to digitally compromise its very core, making our digital lives inherently more secure, all without you ever seeing or paying for an extra component.
Wow. So your smart lock could feel someone trying to glitch it.
Exactly. Imagine your smart lock not just being password protected, but instantly knowing if someone is trying to glitch its internal chip to bypass its security. Or a medical implant being able to sense a malicious EM probe trying to extract your health data.
That's kind of mind-blowing. The security is baked right in.
Baked right in. It opens up a fascinating realm of possibilities for a truly self-defending digital ecosystem. So here's a thought to leave you with. What other invisible security features might be built into our devices that we don't even realize, silently watching and protecting us at the microscopic level? The future of security might just be about making our devices self-aware, and this research is a powerful first step in that direction.
That's a truly thought-provoking idea to leave with. Imagine a world where your devices aren't just performing tasks, but are actively, subtly protecting themselves at the most fundamental level without any intervention from you. It's a powerful vision for a more secure digital future where our trust in technology is truly earned by its own intrinsic defenses. Thank you for joining us on this deep dive into the hidden world of on-chip guardians. We hope you'll continue to explore the ever-evolving landscape of technology and security with us. Stay curious and stay secure.